Ladies and gentlemen, welcome to this presentation. My name is Florian Kalkowsky. I'm a member of the working group Mechanical Joining Technology at the Fraunhofer IGP Rostock, Germany. And today I'm here to talk to you about the experimental investigations on the design and execution of shear-loaded blind rivet joints in steel lightweight constructions. During this presentation, I want to talk about the shown points. First, I want to start this presentation with some application examples for connections with blind fasteners. Go on with the design rules according to the Eurocode 3 for the design of such connections. Go on with the determination of static values by experimental based and design, followed up by the determination of the shear resistance of blind rivets and bearing resistance of blind rivet connections, and finally I want to give you a summary and an outlook. Here you can see some application examples of steel lightweight constructions where blind fasteners were used to join the components inside these constructions. On the left hand we can see high-rack warehouses with slim profiles and small connection sizes. With the new field of the renewable energies in such solar power plants, the substructure is joined by blind fasteners, or roof and wall claddings, where the roof or wall cladding is connected to the substructure by using blind fasteners. For the shown lightweight steel constructions and their bearing type connections, static strength verification is necessary, which can be done with the design rules according to the Eurocode 3. For lightweight steel constructions, we have the part 1-3, and for steel constructions, we have the part 1-8. And if we now look on the design equations, we see that for bolted connections, a pure analytical strength verification is possible. In contrast, for the connections with blind rivets, only the bearing resistance of the components inside the connections can be determined pure analytical. The shear resistance has to be determined in experiments, and in addition, this equation to determine the bearing resistance is limited by further requirements, which we can see on the right side. And because of these further limitations, the shown application example are often not covered by the standard. Whenever the determination of static values by experimental based design for connections with blind fasteners is necessary, we have the DIN standard 14589 to determine the shear resistance of the fasteners, and also we have the ECCS recommendation where a test procedure is described to determine the design resistance of connections under shear load. There are further other specifications, but they are based on the ECCS recommendations, so I do not want to go into them in deep. In the absence of a design rule for determining the shear resistance of blind fasteners, tests were carried out with the aim of determining an adaptive quantity equation. This equation should enable a pure analytical verification in the future. For the test, we used our test machine Zwickwold Z400E and the test arrangement according to the DIN standard 14589. And during this test, different parameters were varied. For example, the type of the blind fastener, the hole diameter, and the position of the shear plane. As a result of these investigations, we could develop an adaptive quantity equation for multiplied types of blind fasteners, as shown here on the right side. This equation allows a pure analytical calculation of the shear resistance as a function of the diameter. Already mentioned, the procedure for determining the design values for lightweight steel connections is described in the ECCS recommendations. The tests were carried out on our test machine Zwickwold Z400E with the test arrangement according to the ECCS recommendation and the described test procedure where A test speed of 1 millimeter per minute is defined, and also a free measuring length of 150 millimeter to determine the displacement during the test. The connection was a one-sided connection with a plate thickness combination of 1+1. And for the evaluation of the test results, we used the procedure according to the ECCS and compared these results with those according to the standards. So you can find in the diagram the lines for the bearing resistance of the components according to the Eurocode 3 part 1-3 and also for the part 1-8. And in addition, you can find all detailed photos which show the connection at different times of the test, and we can see with the increasing displacement which was measured in the connection, the inclination of the blind rivets also increased, and because of this it cannot be assumed that there was a pure bearing failure of the component, and this is clarified by the comparison of the design values. The evaluation according to the ECCS provides the lowest design value, and this means no separate verification according to the standard, the Eurocode 3, is possible. We performed additional tests with one-sided connections, but this time the sheet thickness of component 2 was minimal 2.5 times that of component 1. This change was made on the assumption that this would suppress the inclination of the fastener, which we have seen in the test before. We also systematically changed the edge distances and load direction until the failure of the connection changed from bearing failure to shear failure of the blind rivet. And with the maximum load from the test where we had bearing failure of component 1, we determined the load bearing coefficient, and this value was then related to the design quantile of the Eurocode 3 part 1-3 and 1-8 for bolted connections, and the location of the test point shows that a safe design is possible according to this design rules, also for connections where we use blind rivets or blind fasteners in these connections. Let me summarize again the points we have looked at in this presentation. We presented new design rules for connections with blind rivets. First, we had the adapted quantity creation for multiple types of blind rivets, where we can determine the shear resistance as a function of the diameter full analytical. The second point was the bearing resistance of the components inside the connections, where we showed that the formulation from the Eurocode 3 part 1-8 of bolted connection is also applicable for connections with blind rivets if we have specific connections geometries. And with this new design rules, we can do now a separate verification of the blind rivet and the components. In the outlook, it should be mentioned that the new design rules are limited to an ultimate strength of the components of 550 Newton per square millimeter. So the field of high-strength steel applications isn't included in this new design rules and needs more research in the future. And also the fatigue resistance with a specific detail category for the blind fasteners and the connections are or is an open point that the authors want to address. like to thank the European Research Association for Sheet Metal Working and the AIF, which funded this project. And additional thanks goes to all our project partners which were involved and supported us during this project. Thank you very much for your attention. If there are any questions, please do not hesitate to ask. You are also welcome to send us an email afterwards. Thank you.